hydrolysis reactions, right? So you should be able to complete that workshop on hydrolysis reactions. That's the expectation, is that you're going to go in and you're going to complete part A, part 1, whatever it's called, of the part A of the workshops. Okay? So just to remind you of a few things, right? The amide hydrolysis is reversible both in acid and base conditions, and the ester hydrolysis is reversible in base conditions. I mean, it's irreversible in base conditions, but reversible in acidic conditions, right? I wanted to start by talking about hydrolysis of those amides in base conditions. Okay? This is related to the homework. Oh, by the way, right, homework. There are 2 corrections to the homework, which I'm glad to see no one turned it in today. You all recognize it's due on Monday. That was good. Okay, so on problem 6, the formula was C6H12O. And Daniel, I can't even remember the second one now. What was the second issue? No. There is one that is chemical shifting 5. That's weird. I agree. But no, there's another correction. Okay, I'll think of it. I'll find it. Don't worry. Okay. So look for the other correction here. Yeah.
If we can't see like the carboxylic acid, the red stretch down there, then we don't need to. There's nothing there, right?
Okay. If all the peaks for the important entities are shown. So if the NMR is cut off at 8 or whatever, that means there is no aldehyde, which would be at 9 or 10, or no carboxylic acid, which would be at 10 or 12, right? So, okay, there is one more. I will find it, okay? And I will put that correction up here, and I'll make note of the correction when I put it up here, okay? So pay attention later on. So I just reminded myself that, yeah?
Did you change the NMR spectrum too?
No. Okay, let me look at this. I am seriously just working from memory. When you guys get going on the workshop, I'm actually going to bring up the homework and stop working from memory and start working from the actual paper. So that might be a good start, right? That'd be a good start. So I'll do that. So just wait on this, and I will put the corrections up. My point is there is at least one, there may be 2. I will make announcement of it, okay? And I'll send it out over email as well. So they're due on Monday. If you can, print them onto 2 different sheets, not double-sided, because unbeknownst to Kim, she's grading one of the sheets and I'm grading the other. So we're going to split the pile into 2. Everyone understand that? Okay. So this is related to the homework, right? The amide hydrolysis in base conditions, okay? What I do is I really tag off this piece, right? Because in hydrolysis, this piece is going to stay steady. It's going to be there in the presenting or the carboxylic acid that's generated in the end. Now, if I say had something like this, and this example is really quite important, it's going to be this piece only that becomes the carboxylic acid. What's going to happen is I'm going to get an OH on this side, right, as the amine falls off, and an OH on this side as the amine falls off. That creates H2CO3, and H2CO3 is actually CO2. It's dissolved CO2, right? That's the buffering system that you have in your blood, okay? So you should be looking for something like this. Now, when I do base hydrolysis, okay, of this, my first step is going to be attack at the carbonyl of the base, right? Because we either have a good nucleophile, that's the OH minus, that's always true in basic conditions, or I have a good electrophile, that would be the protonated carbonyl, and that is true in acid catalyzed conditions. But I have to have one or the other. I'm in basic conditions, so my nucleophile is doing the work. It attacks at the carbonyl center, I push up electrons to the oxygen, and now I have come down to this here. Now, one thing we're always thinking about as we collapse the carbonyl is to lose the best leaving group. Okay? That's sort of the argument we're going to be taking today. We lose the best leaving group. So I consider all the potential things that can lose, right, or can be lost. And I consider the conjugate acids pK pKa of all those potential levers, and I choose the best leaving group based on finding the weakest conjugate acid. Okay? Now in this case, it would be pretty obvious that the OH minus getting lost would be the most obvious, which would make this step reversible. But if 1 in 1,000 times, which really, it might be 1 in 10,000, I really don't have the probability on it. My point is, if once in a while, instead of losing this OH minus, I lose this NH2 minus, which is a possibility, right? These are reactions that are ebbing and flowing, and the least likely step can happen sometimes, right? That's just the nature of the beast. I'm going to come down to this and have let go of NH2 minus. NH2 minus is a fantastic base, right? Its conjugate acid is NH3. Fantastic base. It's in solution with an acid, a pretty good acid, a carboxylic acid. And immediately, I'm going to have an exothermic acid-base step. An exothermic acid-base step that's going to lead to the presence of carboxylate, so an O minus here, and the neutral amine. And there is no back reaction here, because the carboxylate is the worst electrophile that we have, right? We already said that it's below the amide, right? Whenever we wrote these, I'm writing them left to right today, right? We put the neutral carboxylic acid on par with the ester, but we put the carboxylate even less reactive than the amide, because it has a negative oxygen, and that electrophilic center isn't going to carry, that carbonyl center isn't going to carry a good positive charge. There's a negative charge right next door. So in essence, we have now the inability to move back, okay? There's no attack at the tetrahedral center. There's no acid-base chemistry that's going to move us back. And what happens via Le Chatelier's principle, right, is that I begin to draw off this intermediate. And eventually it all pulls to forming this product, okay? So it's formed from a very unlikely step, but this unlikely step leads to such an exothermic acid-base reaction that this is the direction of the reaction. Does everyone understand that? Yes.
We had to pull off water for like the ketone formation. Do we have to do anything to
No.
keep it going in the structure? It just doesn't.
No. Yep. Okay. Yeah.
So only that first step is reversible, but then depending on which way the reaction goes, if the NH2 leaves, that makes the rest of it irreversible.
Exactly. Exactly. Yes. Okay. So I wanted this noted. If you're having trouble with that still, please do stop someone and ask someone about the homework as well. We're happy to answer questions about that. Okay? Yeah?
Can you just repeat why it would go through this route?
It's not likely to, right? That's the problem. But when it does, it's the exothermicity of this last acid-base reaction that in essence pulls the whole reaction this way. It's just the unlikelihood, right, that leads to such an exothermic reaction that in essence pulls the reaction in this direction, and there's no going back. Yeah?
Under acidic conditions, would you protonate the oxygen or the nitrogen?
Under acidic conditions, you generally protonate the carbonyl oxygen, and that's all based on the resonance structure issue as well, right? That protonating the carbonyl oxygen leads to 2 resonance structures, and protonating the nitrogen of the amide leads to only 1 structure, period, no resonance structure. Okay? Every time, we're always going to protonate that carbonyl oxygen in acidic conditions. First step, always. Okay? Yeah?
So if this happens and you form that carboxylate, how do you make the H2CO3 in that reaction?
Okay, great question. I was wondering if someone was going to ask me that. So that's great. I'm going to answer it because it's a good question. So this, in essence, right, in the solution that it's in, could certainly be protonated, right, in some cases by other things that are floating around in solution. So think about that. There are other things floating around in solution, and there is where it's going to come from. Okay, good question. Okay, all right, so today we're turning the tides and we're moving on to the next section of carboxylic acid derivatives. So the first things that carboxylic acid derivatives do is they hydrolyze back to the parent carboxylic acid. That's number 1. So understanding those hydrolysis reactions and the mechanisms and the reaction conditions are the first sort of unit in carboxylic acid derivatives. The second unit in carboxylic acid derivatives are what we call interconversions between the derivatives. Okay? Now, there are a couple things that we want to get out of the workshop today. Okay? So, in no particular order necessarily, okay? We want to understand that you can only move this way for substitutions. Meaning, I can make an acyl chloride into any of these other things. An anhydride, an ester, an amide. But I can never make an amide into anything else in one direct step. Okay? I have the table written today left to right instead of up to down. So if we thought of it in the up to down version, top to bottom, that I usually have, the concept is I can convert any molecule in one step to something below it in the table, but I can never move up the table in one step. I can never move up the table in one step. All right? So that concept is one thing that we're putting out today, is to recognize why you can only move down the table. And your homework, problem 9, is actually looking at that as well. It's testing your ability to recognize you can only move down the table and never up the table. There should be 1 or 2 reactions in that problem 9 that should have no reaction, because they're asking you to convert something lower in the table to something above it in the table, which cannot happen. Okay? We're going to be talking about this. I'm going to actually show you 2 reactions here in a minute. So that's number 1. Substitutions only move in one way, or a single step reaction. The second piece is to understand what you need to add to make the substitutions. Okay? So, if I want to convert an acyl chloride to an anhydride, which is the only one, right, that I can make an anhydride in one step only from an acyl chloride, this is the piece I want to add. Now, it seems the most obvious that I would add something negative. I would take, to do this conversion here, I would add this piece here, right? That is the most obvious, and it works for this conversion only. It does not work after this. After this conversion, we only use neutral nucleophiles. And that is related to the acid-base chemistry that can happen with these molecules. Okay? That alpha site over here is actually mildly acidic, right? We've talked about that before. Those alpha sites are mildly acidic. So I've got to be careful about the bases that I use. So if I look at, say, something like this, with acetate, it's not going to pull that proton. When I do acetate here, it's not a strong enough base, and this type of reaction is only going to do the acyl substitution. If I tried to take this and add OR minus, which if you come back with me and think logically, if I wanted to convert the acyl chloride to the ester, right, you would think, okay, I'm going to add OR minus, right? That would seem logical. The OR minus is going to do acid-base chemistry. It's going to do acid-base chemistry competing for acyl substitution. So really, it's a competitor. So we don't want to do that. We don't want to have any heavy competition between 2 reactions, right? So we aren't going to add OR minus when we do our conversion here down the line to do this conversion. I want to add HOR. I want to add the neutral alcohol. Okay? So that's true for any of these conversions. For an acyl chloride to this ester, I'd add a neutral alcohol, making sure it has the constitution of the OR group with a neutral version, right? The protonated version. Same thing with the amide. Never going to use the negative base. I'm going to use the neutral amine to convert to the amide. And it's true if I start with the anhydride to the ester, I use a neutral alcohol. The anhydride to the amide, I use a neutral amine. The the ester to the amide, I use a neutral amine. Everything's neutral except for this very first conversion because acetate or carboxylate isn't strong enough to deprotonate that alpha site. Okay? All right. The last piece to sort of capitalize on is the leaving group propensities and the concept of yield. Okay? Leaving group propensities become pretty obvious as we talk through the mechanism, but the yield is a little bit less obvious. Okay? I'm going to give you the general rule of thumb first because I think that's helpful, but I want you to understand the rule of thumb, which is why we're doing the workshops. Okay? If I do a one-step conversion, going down one step in the table, I only need 1 mole of a nucleophile to make the reaction happen with good theoretical yield, a mole-to-mole conversion. So, acyl chloride to an anhydride only needs 1 mole of a nucleophile. An anhydride to an ester only needs 1 mole of a nucleophile. An ester to an amide only ever needs 1 mole of a nucleophile. Okay? That allows for mole-to-mole conversion, 100% theoretical yields. If I go 2 steps, which in this case would be the acyl chloride to the ester or the acyl chloride to the amide, I need excess. I need excess nucleophile to ensure complete conversion, to ensure 100% theoretical yield. And that would be true for the anhydride to the amide. Excess is necessary. 2 steps on the table requires excess. So I'm going to go through a 1-step conversion and a 2-step conversion here, just so you can see this. Okay? So let's start with our 1-step conversion. We'll go ester to an amide here. So my 1-step conversion, our example will be an ester to an amide. The amide sits right below the ester. I can convert the ester to the amide in a single step, but I can never convert the amide to an ester in a single step. Cannot do it. I'm going to prove that here, and then we're going to agree that we can't work up the table. So let's make up an ester here. Okay, so here's an ester, and we want to make an amide, so so we'll go to this one. So the first thing I do is I think, what do I need to use as my nucleophile? So as my nucleophile, I need to use this piece as a neutral amine. So I'm going to fill in my reaction conditions so I make sure that I get that right. So I'm using this, just ethylamine, right? Every nitrogen wants 3 bonds. It has the ethyl group, need that. Then it's going to have 2 hydrogens, right? So ethylamine. So now I'm going to show the mechanism. The amines are always weird, right? Because they're these moderate nucleophiles, and we never sort of appreciate that. We don't need any acid catalyst. We do see reaction here to this site, okay? So, mechanistically, as this attacks, I get a tetrahedral intermediate, right? The tetrahedral intermediate has that O minus, it has the OR, and now it has this nitrogen group on it that's positively charged. We're not in acidic or basic conditions, right? So we can just add the nucleophile. If I don't specify any acid or base conditions, this is what you get. Okay? We know that this can come on and off, on and off. Okay? We also know that this needs to be deprotonated. Now, the first bunch of steps through, and actually the amine is always a good base, the amine is the best thing to sop up any of these protons. So now, while I put in a mole, perhaps, of my amine, some of it's going to be used as a base here, right? Because this is what's going to be around to deprotonate this intermediate. Okay? This is what I have. Eventually, I'll have some alcohol there, right? Some OR minus. So that can be used eventually, but initially, this is what's there. Think about it logically. You have your intact ester, you have at least a mole, right, into the amine, right? So in essence, what you're going to create out of this is some of this. This is no longer allowed to behave as a nucleophile. Any population of amine that's sidelined to behave as a base, in essence, doesn't allow it to act as a nucleophile. It takes some of that nucleophilic population away. Okay? So I wind up now with this protonated version of my nucleophile of choice. And now here, my tetrahedral intermediate, which can collapse. Now, I know that this will collapse down, and my most likely leaving group is this guy. Okay? If the nitrogen falls off, it's coming right back on. There's no acid-base chemistry that can happen there. So if the nitrogen falls off, it's coming right back on. All right? So in this case, really, this is what happens in general in this reaction flask. So what we get out of this is now our amide, right? And our leaving group, the and, okay, which was ethoxide. Now here's the question we ask. Is ethoxide going to rescue the nucleophilic population that was made into that conjugate acid? Meaning, what is the acid-base reaction between the leaving group and the protonated nucleophile? And that is always the acid-base chemistry you're going to look at. That's a golden rule. You're always going to look at the acid-base chemistry between your protonated nucleophile, that's this NH3+, and your leaving group. Okay? So I'm about to analyze that acid-base chemistry. I'm questioning whether or not the leaving group can rescue the nucleophilic population that I need to sustain in order for a complete conversion. So here's my leaving group. Here's my protonated nucleophile. And I get out of that a neutral alcohol and a neutral amine, right? This is what I get out. This is my acid-base chemistry between my protonated nucleophile and my leaving group. This is 9.4. This is 16. Which way does the reaction go? To the right. That means, really in the flask, as these two meet, this is what I get. Neutral alcohol, neutral amine. That means that I don't have to worry. Eventually, all of my amine is going to become neutral again. I'm going to have a complete mole in the flask, in essence, of neutral amine that's going to convert now into the amide. Okay? With these one-step conversions, I've told you, you do not need excess nucleophile. The reason is that your acid-base reaction between the protonated nucleophile and the leaving group will sit to the right. This is the theoretical reason why we only need a single mole of amine. When the acid-base chemistry between the protonated nucleophile and the leaving group sits to the right, we only need a single mole. Yeah?
And that would be because our leaving group rescues the nucleophile.
The leaving group rescues the nucleophile. That's right, like a knight in shining armor. Okay, so let us look at a two-step conversion, and then we're going to move on, and you're going to try some of the workshops. Yeah? Why? I can't hear you. A catalyst. Why doesn't it need a catalyst? That is a great question, and the reason it doesn't need a catalyst, actually, is because the nucleophile itself is moderate. All the other nucleophiles that we generally present are not, which is why it goes. Okay? All right. So this would mean we can do something like an acyl chloride to an ester. All right. So let's take an acyl chloride. Remove that arrow. To an ester. So this is the reaction I'm going to look at. maybe say is this guy. The first thing I want to do is say, if I want to make this conversion, what's the nucleophile I need? So I identify this as what I'm swapping out, right? That's what I want to add. And instead of being O minus, it's going to be OH, right? Neutral. So I know that I'm going to add this. This is the alcohol that I'm going to add to make this ester in the end. Okay? So now we go through mechanistically, we start looking at it. So we have direct attack at the carbonyl center and the formation of a tetrahedral intermediate that has now the Cl and the alcohol. When the alcohol's on, it's protonated, right? Neutral nucleophile. So I need to deprotonate that before anything else happens, right? It's always the next step after a neutral nucleophile is added. Always the next step. What do I have in the flask to do that deprotonation? I have that alcohol, right? And truthfully, that's the best thing in solution to do the deprotonation. So it comes and deprotonates. Same concept. I am pulling off some of my nucleophile here, right? Into this guy here, and this is not a nucleophile. It's got a positive charge. It's not a nucleophile. So I'm drawing off some of what I'm adding, so it serves as a base. And hence, I don't have a full mole for complete conversion, right? Because I'm not, the full mole I'm adding isn't doing all of the work, right? So we come down here. We're now at the point where this no longer is going to come on and off, on and off, on and off, right? Now we're at the tetrahedral collapse. So I pass down. I think about what the best leaving group is here. Clearly Cl is the winner. Okay? You've got to think about your leaving group propensities. I compare the conjugate acid of Cl minus to the conjugate acid of the isopropoxide to the conjugate acid of this negatively charged carbon nucleophile, and I come up with Cl being the best leaving group. So what I get out of that now is the ester I wanted and Cl minus. And I question, can Cl minus rescue this conjugate acid here? So I come back and I do the same thing. I look at the acid-base chemistry between Cl minus, the leaving group, and the protonated nucleophile. And this forms HCl as its conjugate acid, and isopropoxide, nope, isopropanol, sorry, lie. Truth. Okay. And I look at the conjugate acid on each side. This side is -2, roughly 2.5, right? This is -7. Which way is this going?
Left.
To the left, right? To the left. And hence, that means that Cl minus cannot rescue my nucleophile population. So, the question of, do I need more than a mole? Yes, you do. Because some portion of that's going to serve as a base in solution, right? In essence, you really need 2 moles, roughly. One serves as the nucleophile, one serves as the base. Okay? All 2-step conversions should lead you to an acid-base reaction between the protonated nucleophile and the leaving group that sits to the left, which is saying, I can't rescue the nucleophile, and hence, you need to add excess in order to make that happen. Okay? All right. So we're going to pull out the workshop. You're going to start trying to work through some of these on your own. You forgot your workshop. You need some extras. There's some here. You can come get one. That's totally fine. Okay?
Dr. Dixon, I'm just curious. Why can't the negative oxygen take the positive oxygen's hydrogen? Could that ever happen?
Generally, no, because we don't actually have them in. It seems like, right, when I do a mechanism, it seems It's like I make this, it stays around.
I mean, you can just go
I
to
make
yeah,
this, it
let's-
stays around,
it's the
right?
same as
It's not really actually what happens. It's all happening too fast. And so because of that kinetic profile, it doesn't actually, doesn't exist for a large proportion of the time. Now here, this is another kinetic argument, which is actually an interesting one. Because of the way that molecule is, for it to meet and serve in that capacity is actually really hard.
Does that require a lot of energy? That's
It
why.
does, because in kinetic theory it says that we have to meet with the right orientation and the right energy. So the meet is hard.